Hello everyone. In the last two lectures, we have seen how we can formulate recurrence relations, and also we have seen there how we can develop mechanisms in order to solve first order and second order homogeneous linear with constant coefficients and with little bit of variable coefficients as well. So primarily we have seen for the second order recurrences, we have to find out something called characteristics equation. And we have to find out the roots of the characteristics equations in order to see whether the roots are distinct real, equal, or maybe complex conjugate pairs. And accordingly, we treat them as linear independent form of solutions and add those solutions to get our final answer. And finally, we have seen that there are techniques for removing the constants through the base conditions where we try to solve for the constants. So to everything put into a generic format, for higher order, we have this kind of recurrence relation where there are nth term depends on all previous k number of terms. So that is from n minus 1 up to n minus k, where n is greater than equal to k and k is a positive number. So we say that a recurrence is of order k if this is valid. And we are considering with homogeneous recurrence, so my fn will be equal to 0. The terms are linear with constant coefficients. Here C0 not equal to 0 and Ck not equal to 0 are the real constant conditions, because to make it kth order, these two terms must not be equal to 0. As we have seen in the second order, C0 and C2 was not equal to 0. And the boundary conditions we found out is that Tj equal to Dj, that is T0 equal to D0, T1 equal to D1. So in second order, we have two boundary conditions, T0 and T1. For kth order, we need k boundary conditions to solve our constants when we go for the solution. So these boundary conditions are required. So T0, T1 and up to Tk, where every Dj is a constant. So if you remember, for the second order, we can generalize the characteristic equation up to kth order. So by replacing Tn equal to C into x to the power n, which gives rise to this kind of a equation, and if C and x are not equal to 0, then we get the equation as x of the order, x polynomial of the order x to the power k. So C0 x to the power k to Ck x to the power 0. So this is equal to 0. And if we solve it, as in case of second order, it's a quadratic equation, so we get two roots. So in case of kth order, if we solve it, we will get k number of roots. So each root will satisfy the condition that if we put in the characteristic equations, it will give me 0. So each root will satisfy this, and once we get such roots, among them, some of them could be distinct real, some of them could be equal and real, and some of them could be complex but having a conjugate pair also in the roots. So we have seen that if we get each category, we can formulate linearly independent answers and can add up to get the final recurrence. Here, if we get three categories of such roots, then also we could, due to linear independence of those formulations or solutions, we could add up and then finally give Tn as the added solution. Let us see how. That first we know that we have u number of real distinct roots among these k. We have v number of complex conjugate pair of roots, so total 2v number of such roots, including the pairs everyone, and w number of roots which are identical. So therefore, the total roots will sum up with all this, and we need certain constants to express the following. For real distinct roots, we have used such roots, therefore I denote it as R alpha 1, R alpha 2 up to R alpha u, where each alpha I, alpha 1, alpha 2 and alpha u is in between 1 to k, because I have R1 to Rk, so I just have any arbitrary index could be a distinct root. Complex conjugate pair, there could be exactly v number of such, so I have r beta 1 as the plus x plus iy and r beta 1 dash as x minus y iy. So similarly, there are v such pairs. So this in the r theta coordinate, I could express it using r cos theta plus minus I sin theta, and for each of them I just did this index. So these are my complex conjugate pair of root expressions, and for the real roots, equal and real roots, we have a single particular value equal to every w number of such. So when we have all three possibilities, we will try to determine solutions for each of them, and due to linear independence, we will just add them up. So this is how we do. Earlier, in second order, since there are only possibility of two roots, so either it will be distinct or it will be equal or it will be a complex conjugate pair. So either this brown part we did, or this blue part for the complex, or this red part for the equality. Brown part says that every root that you are getting here, which are distinct, you try to have a1 r1 to the power n plus a2 r2 to the power n in this format, which is for the distinct roots. This one is for the real roots, since this one is for the complex roots. Since the complex roots are also different, so therefore I can have the same kind of formulation going between them. The only thing is the elimination of I, which I have already shown for second order. I will generalize it here in the next step. This one, since you have w number of such roots which are same, so due to linear independence being applied, we need to have something called n into r gamma to the power n, then n square into r gamma to the power n. As in the earlier case, we have shown for k such equal roots, we will do that a1 plus a2n plus a3n square up to a w minus 1 n to the power w minus 1. A w n to the power w minus 1. So this sum will be for the equal part. So all of them added together due to linear independence give me the solution for T. And for the r theta coordinate, if I transfer the complex conjugate root, the same will be transferred to this. Others remain the same. Only this one for the complex root I have done, where my b beta l is a beta l plus a beta dash l, and b beta l dash is equal to a beta l minus a beta dash l into I, where I is root over minus 1. So this is for the second order. We have seen it. Just this slide looks clumsy, but what I have done is that I have made it for k number of roots, and a chunk could be distinct, a chunk could be equal, and a chunk could be complex conjugate pair. Since linear independence rule we can apply, so we can club them up and find the final solution. Where we cannot apply linear independence, if there are equality in those roots, and if that is the case, then indeed we have to go for gn into r gamma to the power n, as we have shown, and we just did it here, n into r to the power n, n square into r to the power n. This is the simplest function we can append on. So with that information, let us see an example for the third order such recurrences. Again, we revisit the tiling problem, but here we give two different types of dominoes or tiles to tile it. So there are, so Tn is the number of ways we can tile 2 cross n chessboard, and we are given with an L-shaped tile. So 2 cross 2, only 1 cross 1 cell missing, and a 1 cross 1. It looks like this. These two tiles are given. You are given to tile this 2 cross n chessboard. Now, how many ways you can contribute to Tn? One is that if you use only 1 cross 1 tile, then you can place it in these 2 squares, and the remaining 2 cross n minus 1, you can recurse by saying that I have Tn minus 1 way. This is my case 1. The case 2, I will use only L shape. If I use only L shape, I have this is one possibility. So it takes up 3 columns. So there are Tn minus 3 number of ways the remaining can be done. This is another possibility where I just have a different orientation to place the first L. Again, Tn minus 3 will be another combination. So case 2 gives me 2 into Tn minus 3 number of combinations contributing to Tn. What is case 3? That I will use a mixture of these two. So one way to use a mixture is that put the square here, 1 cross 1 cell. Put this 1 cross 1 cell in bottom left, top right. So there are 4 possibilities in which you can cover 2 columns. The rest is n minus 2. So Tn minus 2 ways to do it. So each of them results in Tn minus 2 ways. So the case 3 type of tiling takes you to 4 into Tn minus 2 ways to completely tile the whole thing. Now, adding up is my recurrence. So the recurrence relation says the number of ways to tile 2 cross n is the number of ways to tile 2 cross n minus 1 if I tile it initial positions this way. Then 2 into 2Tn minus 3 if I only use to tile the initial positions, and then 4 into Tn minus 2 where my T1 equal to 1 because I have, if I have 2 cross 1 cell, I can only place 1 cross 1 squares. T2 equal to 5. If I have 2 cross 2 cells, then I have 1 cross 1 cell placed 4 times, or all these 4 gray combination, gray part of it. So there are only 5 possibilities. Similarly, T3 will be 11, you can compute it. So since it's a recurrence of third order, we need these 3 base conditions to eliminate our constant. Now this will give me the characteristic equation as xs cube minus x minus 4, xs cube minus x square minus 4x minus 2 equal to 0. If you solve it, you will get R1 equal to minus 1, R2 equal to 1 plus root 3 and R3 equal to 1 minus root 3. So I get 3 different roots, all are distinct. Now I apply that A1 R1 to the power n plus A2 R2 to the power n plus A3 R3 to the power n and solve using T1, T2 and T3, all these 3 constants. You will form 3 equations with 3 constants to solve. You will get constant A1 is equal to 1 and A2 and A3 are 1 by root 3 and 1 by minus 1 by root 3 respectively. So your final recurrence will be this, and you can verify by putting T equal to 1 here, getting this. T equal to 2 will give you this, and so on. So this is an excellent example that we could just change the shape of the tiles, and our 2 cross n chessboard tiling problem gives us a third order of recurrence where my order is of 3. Now you can also see that we could also build higher order recurrences. Let me give you a verbal example. If you try it at your home, that instead of tiling using these 2 sets of tiles in the 2 cross n chessboard, you try to tile it using 1 cross 1 cell, like this kind of a square, 1 cross 2, that is this 1 width and 2 length rectangles, and 1 cross 3, that is 1 width and 3 length rectangles. Try to figure out the recurrence, you will find it is much higher order than 3. So I want to see that how many ways I could tile a 2 cross n chessboard using 3 tiles, 1 cross 1, 1 cross 2 and 1 cross 3. Later you will see, you will be amazed to generalize this by going up to 1 cross L such rectangular tiles. So first you try with 3 tiles, then you generalize, you have L tiles, each are of 1 cross L minus 1 up to 1 cross 1 rectangles, and then you need to tile the chessboard of 2 cross n. See how the recurrence, order of the recurrence changes, and try to have a generalized solution and generalized recurrence form for that. Finally, you will be amazed to also work out your calculations further to have it on a generic chessboard. Like instead of 2 cross n, if I say I will give you m cross n chessboard, with these 2 tiles, how does it go? In the previous problem, we only give 1 cross 2 and 2 cross 1, one type of tiles, how does it go? And if I give you 1 cross 1 to up to 1 cross L, this L type of tiles, how can you tile? So please try all of these at home, and this is your homework for this semester, that you will be amazed to find the closed form recurrence relation, generic recurrence relation for this, and the solutions or the closed form formula for Tn that you can get from here, or Tm comma n in the other case where you generalize m and n rows and columns. So all of these we have discussed till now, either first order or second order. We primarily considered the homogeneous case, that is the function is 0. There is no added function apart from the terms with constants. See, in this example also we haven't added any function. But in generically, if we have a non-homogeneous reference, so for the first order non-homogeneous linear recurrence, we have seen in the first lecture that if there is a formula that comes out which sums your Fn, so this is my Fn which sums up with that. Now if I have a closed form expression of that formula, I am done. But many cases you will find that such a formula doesn't exist where you can get the summation as a closed form. So therefore you could have alternative way to find out the solution. Here is how we go about that in a generic way. So for first order linear non-homogeneous recurrence with constant coefficients, which is of this form, linear because the terms are linear, constant coefficient because all recurrent term has constant coefficients. Non-homogeneous because the function it has is non-zero, added to the recurrent terms, with a base condition equal to D. Your B and C could not be equal to 0 because otherwise your function is homogeneous. If your B is 0 and C is 0 doesn't mean that it is a first order recurrence. We will try to solve it in two parts. One is the homogeneous solution part, which we will assume that as if we do not have any function here, it is 0. So this is a homogeneous part, and you can easily see from Tn plus Ctn minus 1 equal to 0. As per our previous concepts, we can easily derive that it is a formula which is a constant into minus C to the power n. Remember, here I cannot supplement Tn0 with D because this is the homogeneous part of the solution, not Tn itself. So therefore, T0H may not be equal to T0 because T0 also contains the total part of the solution, not only the homogeneous part. So we will derive this constant A after we get the full Tn expression with us. So now let us consider another part of it, which says that if this be the format of my answer which I get from Tn and Tn minus 1, what if my solution is of this format, that is some constant into b to the power n format? So if that is the case, there could be two possibilities going. That your particular solution, looking at the non-homogeneous functional addition, I am seeing that Tn plus Tn minus 1 gives this format. So why not I just seek a solution of that format for a particular part. So this particular part solution will say that I have a1 b to the power n as my solution if your b to the power n is not equal to minus c to the power n. Which means that if this is the case, then what I am trying to do is that I am trying to get out the non-homogeneous part of the solution and trying to append with the homogeneous. But if b to the power n equal to minus c to the power n, and if I do not change it, then this will not be linearly independent. As per our previous experience, we have seen to make it linearly independent of similar type of nature of, let's say it is 3 to the power n and you also have 3 to the power n in b. So therefore, I have to do n and append a function gn, that is n into b to the power n, to be the simplest form of particular solution. Now once I did that, my aim is that whether I can get a t to the power n function which can have a solution like this. I can put directly this into my equation and solve for a1 and a2 respectively. Because I am thinking of this particular solution as a mimic for Tn and Tn minus 1. So essentially my Tn would be finally this one. However, this is my particular part, the right side part, and this is my homogeneous part, because homogeneity will also result a part. b to the power n not equal to c to the power n is this, or b to the power n equal to c to the power n is this. Now solving for a1 and a2, I can just directly put, assuming that the particular solution will give me directly answer for Tn. So a1 b to the power n, c a1 b to the power n minus 1 for the first case of particular solution will give me a1 equal to kb by b plus c. Because you have b to the power n not equal to c to the power n, therefore both terms are present. Here b to the power n equal to c to the power n, then you just replace it your Tn by a2n b to the power n, and you will see that there are only one term present, that is c to the power minus c to the power n or b to the power n, any one you can get present because both are equal. And amazingly, this equation reduces to a2 equal to k. So finally, if we put this a1 and a2 as this form here and try to solve for a, which is our homogeneous constant, so then my tnh plus tnp is this one for the first case, where a1 is this one and t0 is d, so I put d here, so d equal to a0 plus a1, because n equal to 0 means it is a plus a1. So a equal to d minus a1, which will be this. And for the second case, if I put the in the final solution here n equal to 0, so it will be a equal to d. So my final solution will be, I just replace the constant that I get from a and the constant a1 that I get from the particular solution directly from general form, putting it into general form and find this, and this is what do I get from the solution when b to the power n equal to minus c to the power n. So these two are equal because I can use any one of them. Both are equal. This might looks a little bit clumsy, but when you try to solve it, again I am telling that this will be only numbers. So this will be much relaxed when you try to see it. So let us see some examples where we use such kind of a non-homogeneous recurrences and try to solve it using homogeneous part and particular part, and their linear independency keeps us to add them to get the final solution. See, the Tower of Hanoi problem, if you remember, our recurrence was Tn equal to 2Tn minus 1 plus 1, because you are moving top n minus 1 disk twice and you are moving the largest disk once. With no element in the Tower of Hanoi give rise to zero movement, because you do not have to move anything for it. So now if you try to solve this particular expression, it's clearly a non-homogeneous because there is an added term to your recurrent terms and constants. So the homogeneous part eliminates this added part and try to solve Tn equal to 2Tn minus 1, which is a into 2 to the power n if I go as per my basic first order homogeneous recurrence solution. I see the particular solution, so this is 1, that means it is of the form k into b to the power n, where your k is 1, b to the power n is 1 to the power n. I can write it as 1 into 1 to the power n. So therefore my particular form has a solution that a1 into 1 to the power n. And this 1 to the power n is not equal to 2 to the power n, so it's different. So therefore I could not have to append any n or any gn function here. So this is my solution for particular case. So I get it is equal to a1. So now I see that I can solve this a1 by putting the particular answer directly in my recurrence as we are doing. So this a1 Tn equal to a1 to Tn minus 1 equal to 2a1 plus 1 will give me a1 equal to minus 1. Now the final solution is nothing but homogeneous part plus particular solution part. So it is a2 to the power n minus 1, which is a1 part, with t0 equal to 0, which gives me a equal to 1. Now I can put here t0 equal to 0 to solve for a. So now since a equal to 1 and a1 equal to minus 1, I get tn equal to 2 to the power n minus 1, which I also received when I expanded this Tower of Hanoi prob recurrence and solved it. Second example. How many comparisons do you need to find max and minimum element both together from, remember, 2 to the power n element set? I need how many comparisons I need to find the max and mean both from a 2 to the power n elements in a set. The strategy would be that the recurring strategy would be, let me divide it into 2 to the power n minus 1 length 2 sets. Then find the min max from both sets and then combine the mean versus mean and max versus max to declare the winner and the loser. That is the final min max from each set. So what I will do is that 2 to the power n set elements I divide into 2. Both set I will try to find mean and max. Then the first set max will be compared with the second set max to get the final max. And the first set mean will be compared with the second set mean to get the final mean. So the recurrence relation would be that 2 to the power n elements set max and mean will be computed by 2 times computing the max and mean for n minus 1 element set, because I am computing once for each set, plus the last 2 comparisons that you do for max and mean. And your M1, if you have set of 2 elements, that is 2 to the power 1 element, you only need 1 comparison to declare the max and mean, because one will be the larger, one will be the lesser. So this is also again a recurrence which will occur in our day-to-day programming to find mean and max from a set of numbers. And also the number of steps that we need or comparisons that we need will follow through this recurrence. And as we can see that this is also a non-homogeneous recurrence. So therefore, I have to go for a homogeneous part, which is mn equal to 2mn minus 1, which means mn equal to a into 2 to the power n as previous. Here this is the constant is 2 into 1 to the power n. Again I will see a 1 into 1 to the power n, because 1 to the power n is not equal to 2 to the power n. So due to linear independence I can take this, and Since it is A1, it's a particular solution, and particular solutions, the philosophy of particular solution is that I will put up in this equation. So A1 equal to 2A1 plus 2 gives me A1 equal to minus 2. Therefore, my final answer is A to the power n minus 2. That is the homogeneous part plus the particular part. And then finally what do we get is, if we try to solve it for the base condition, M1 equal to 1 gives me A equal to 3 by 2. Which means that Mn equal to 3 by 2 into 2 to the power n minus 2. Now you try to write your program and try to count that whether this is happening for every n values or not. For 4 elements, for 8 elements, for 16 elements, how many comparisons are you making using this strategy that is declared? And this strategy we call it as an algorithm. So this is how we see that how better is our strategy in terms of the number of comparisons. Our next example deals with strings with digits containing even number of ones. So it says that we have an alphabet going from 0 to 9, that is 10 digits we have there. We want to construct strings of length n such that it has even number of ones. So this formulation is a little bit tricky. See, how can we contribute to the number of Sn recursively? First of all, my nth symbol is not 1. If I see that my nth symbol is not 1. So therefore, till n minus 1, if I have even ones, the number of ways I can construct n minus 1 symbol with even number of ones is my answer. So if nth symbol is not 1, then Sn minus of 1 ways to construct even number of 1 length string up to n minus 1. And since nth symbol is not 1, so any 9 such symbols if I append to each of those strings will also remain my number of 1 as even. So there are 9 such cases where Sn minus 1 number of ways can give me even strings if nth symbol is not 1. If my nth symbol is 1, then what I need from the n minus 1 length? I need that n minus 1 length string to be of odd number of ones, because it will be appended with a 1 to get a total string of even ones. So therefore, now the number of ways I need is how many odd number of ones can I formulate, how many strings with odd number of ones can I formulate of length n minus 1. It is this. How? Because n minus 1 length string, if I try to formulate, and there are 10 symbols, how many possible strings irrespective of even and odd ones can be there? It is 10 to the power n minus 1. Sorry, this will be n minus 1. This is a mistake, this will be n minus 1. So it is 10 to the power n minus 1 number of all possible string of n minus 1 length. How many of them are even? Sn minus 1. Because I define Sn to be n length string of even ones. So how many of them are odd? So 10 to the power n minus 1 minus Sn minus 1 of them are odd, n minus 1 length string. So my total recurrence would be 9 such ways where the last symbol is not 1, and if the last symbol is 1, the number of ways I can construct odd number of strings with odd number of ones in the n minus 1 length, which gives me 8 into Sn minus 1 plus 10 to the power n minus 1. So this is my recurrence, where I have, if the base condition is, this is obviously a first order recurrence and obviously it is non-homogeneous. The base condition says that S1 equal to 9, because of 1 length string I could not have 1 there because it will make it as odd. So we have other 9 possibilities. So now you get a recurrence which is non-homogeneous. Go by our formulation of solution. Homogeneous solution part is 8 n to the power n, considering Sn equal to 8 Sn minus 1. Particular solution part, assume that only, so this is k into b to the power n is this one. So therefore I can say a1 into 10 to the power n minus 1, it is not matching with 8 to the power n. So this is the particular solution. So just put it there in the particular solution into the recurrence to get the value of a1. So it will be 10 a1 into 10 to the power n minus 1, 8 into 10 to the power a1 into 10 to the power n minus 2, and this is 10 to the power n minus 1. This will be this one, a1 equal to 5. Finally, the final solution will be a into 8 to the power n plus 5 into 10 to the power n minus 1, which will give me that if I put the base condition as 9 is 1 equal to 9, then for n equal to 1, so put n equal to 1 here gets 8a plus 5, which means a equal to half. So my final solution is the number of strings of length n with the 10 alphabets 0 to 9 possible where there are which have only even number of ones is half 8 to the power n plus 5 10 to the power n minus 1. So this is how we try to solve the first order non-homogeneous recurrences. Let us consider this one. This is a very interesting example with the concept of your Hasse diagram in partial order sets. So suppose S is a set of n elements 1 to n. PS is the power set of S. So as we have seen in the relation part, that power set of S with the subset equal to relation gives me a poset. Okay, so it is a poset that is reflexive, antisymmetric, and transitive relation is valid, partial order. So I need to find out in the Hasse diagram, since we have edges, directed edges there from nodes. So how many such edges are possible in the Hasse diagram? So this is a very interesting formulation. See, let's say for 3 element set S, there will be 8 element power sets. So how this power set Hasse diagram is constructed? So suppose you have this fragment of the power set and this fragment of the power set. So from each of the nodes, you will just connect to one other nodes if you fragment it this way. So how do I fragment it? I fragment it in a form that I have a subset of PS which does not contain an element 3, and I have a subset of PS which always contain an element 3. So definitely for an n element set, the power set, if I divide the subsets of that power set, that some subset will contain n and some subset will definitely not contain n, then those power sets will be fragmented into 2 equal parts, and you can find out that there will be exactly one edge possible from each part. So the number of edges in n plus 1 length set S and its power set of 2 to the power n plus 1 will be 2 into En, because your En has 2 to the power n number of elements, En plus 1 has 2 to the power n plus 1 number of elements. So each of these elements will contribute an edge, so 2 into n number of edge. So these 2 parts will contribute one edge, so 2 to the power n number of extra edge will be there, and each part has its en number of edges inside its Hasse diagram present. So there are 2 parts, so 2 into en number of edges. So let me repeat what we are trying to do. We are trying to build how many edges are there in Hasse diagram. For a set S of n elements, we have a power set of 2 to the power n elements. That is all subsets of the set. Now when we try to form that, we will try to divide the power set into 2 clusters, one containing the elements n as in the subsets, one does not contain the element n in the subsets. Once we do that, we will see that each such subset has exactly one edge to the other subset of cluster. So therefore my recurrence would be, in this division, I have a 2 to the power n minus 1 number of, so let's say for n plus 1 number of sets, so 2 to the power n plus 1 power set, I can divide it into 2 to the power n number of element power sets. Each power set, each element 2 to the power n will be connected exactly to the other cluster 1 element. So it gives you 2 to the power n number of extra edges, plus you have en edges in each of the subcomponents. So it is 2 into e to the power n. You have 2 subcomponents. We divided into 2 clusters. So this, if you formulate this one, then again it's straightforward. But the only thing I kept this example because this is a classic example. When you go for a homogeneous solution part, you will get it a 2 to the power n. But when you go for a particular part, it is again same as 2 to the power n. You cannot use a1 into 2 to the power n as we used in previous all examples. So there we have to go by introducing a function of n into 2 to the power n to make it linearly independent, and once you do that, you put it here to solve the particular solution constant, and then finally when you come up with the answer, you solve the relational constant A, that is homogeneous relational constant, and you will get n into 2 to the power n minus 1 edges in a Hasse diagram. The final classic example of single first order non-homogeneous recurrence which is called as snowflakes. And primarily this is invented, this concept of snowflake and its counting invented by Koch in 1904. But the basic idea goes like this, it initiates the concept of fractals, which means that creating a substructure by breaking the edges or recreating from its own structure. What does it mean? That I will start with a polygon, and what I will do, I will try to extend the polygon by breaking its edge and introducing a smaller part of the same polygon as a hinge to that edge. See here what I did, I break this length into 3 parts. So 1/3 length, same kind of an same kind of a triangle having 3 edges of same length. I just put it 1/3 length, same edges here, 3 positions. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. So for each edge again, I will put 1/3 of the length of that particular edge and try to put that equilateral triangle there. Equilateral triangle, I put it here also. So therefore it breaks down into this kind of a structure. Again I have so many edges, each by 3 length equilateral triangle I put it. So this diagram of regular polygon gets transformed in terms of it and looks like a snowflake. So it's called a snowflake curve. So we will try to determine what is the area of this snowflake that we are building after n transformations. So let us start with regular polygon, and it's a 3-sided regular polygon with an equilateral triangle. So if we start with this, let us see how it happens. If I assume that each side is of unit length, then first triangle area is root 3 by 4. Straightforward, because it is perpendicular, as half into perpendicular into 1, perpendicular is root 3 by 2. So half into root 3 by 2 into 1 is root 3 by 4. So a 3-sided triangle area. Now when I try to extend it by a transformation of 1/3 length equilateral triangle sitting on each of the edges, then see what happens is that these are the additional area that gets added, and this polygon is again regular, but it's a 12-sided polygon because it's 4 into 3-sided polygon. So 3 sides into each side, so each side now has 2 extra. So since I started off with a triangle, one edge will be merged with here, so additional 3 minus 1, 2 edges will be for each side. So 4 into 3, 12-sided. Now the area has increased by root 3 plus 4 was my earlier area, and it has increased 3 times root 3 by 4 into 1/3 square, because now my size of each of the sides is 1/3. And if you try to compute that, since each of the sides contributed as 1/3, if you try to formulate the area, you will get this equation. Let us try to break again. Come to this part. So now each side is now my 4 into 3 sides, and each side will again add up with, so this side again, if I have a small triangle over it, so each side will be again 4. So 4 into previous one. So 4 square into 3, 48 sided polygon will be this one. Now since this will be the earlier area plus the added area, so what is the added area? Added area is that how many number of such small tiny pieces you have added? You have added 4 into 3 such cases. Earlier you have added 4 to the power 0 into 3, because only you have added 3. Now you have added 4 to the power 1 into 3. However, your dimension has again drastically reduced from 1/3 to 1/3 square, because it is now 1/3 and again 1/3. So it is 1/3 square. So this is your area added to it. So it comes as this. You can go on. The other will be this, the bottom right snowflake that I have shown is of 4 cube into 3, 192 sided. This is the earlier area plus 4 square into 3 number of small triangles have added. Each triangle is of 1 by 3 cube side length, and this will come in. So finally you can now guess what is my recurrence. It is A3 equal to A2 plus 4 square into 3 into this. This is again n. This is n minus 1. Here it is. An plus 1 equal to an. Look at the last one and try to figure out the common generic form. So this is for only one addition I get 4 to the power 0. For 3 addition I get 4 to the power 1. 4 to the power 4 square. So for n plus 1 number of edges, polygons, and after n transformations, I will get 4 to the power n such small things to be added into 3 in 3 sides. Each side is of length of each of the small triangle is 1 by 3 to the power n minus 1, and this is where we start off, and this is my area to be added. So this simplified as this one. Again, this is now a linear first order recurrence, non-homogeneous. It's a non-homogeneous because the function is not equal to 0. Homogeneous part solution, particular part solution. Homogeneous part just says an plus 1 equal to an gives me a into 1 to the power n. Particular part says some constant into 4 by 9 to the power n gives me, let's say, b into 4 by 9 to the power n. Now how do I find b? Just put this in an plus 1 equal to an plus this. When I put this, I get my b equal to this. And when I say that my initial condition a0 is root 3 by 4, n equal to 0 if I put it, so it will be a plus b, that is a plus this into 4 to the power n. So the final recurrence will be a plus b into 4 by 9 to the power n, simplified as a minus this one. And a0 if you put, as I have just mentioning, you can get the constant value of a as well for the homogeneous constant value. So finally, a minus this is 6 by 5 root 3 minus this, which is simplified as this. Now if you put n equal to 1, you will get this. If you put n equal to 2, n equal to 3, I have not computed, just put n equal to 3 and get me the result here. So see that this is a concept of fractal in the form of a snowflake. Now an obvious thing ponders us, we have done it with a 3-sided polygon of regular length, unit length. What if we go for generalization of it? Let's say, so 3-sided polygon gives me 4-sided edge after insertion in each part, because 3 length minus 1 will be added. These many edges are added. So this is just, this 4 comes from the fact that you have a side and you are adding it, you are breaking it into 3 parts, you are adding 2 parts into it and merging one. So therefore it comes as 3-part breaking plus 2 minus 1 is 4. So therefore it is always n plus 1 number of a. So if you have k-sided polygon, you always add k plus 1 number of edges in each part, each side. So for 4-sided unit length regular polygon, it will be 5 to the power n. See the recurrence here that I have just formulated. Here an equal to an minus 1 plus 1 by 4 root 3 this. But how do I have formulated it? This way. An plus 1 equal to an plus 4 to the power n for 3-sided polygons. For 4-sided regular polygon, it will be 5 to the power n. 4-sided regular polygons, since in the 4 side we will just append a hinge, it will be 4. This is the initial polygon's area. So it will be 1 for our square 4-sided polygon regular. This is just breaking it into 3 parts every time, reducing the side length 1/3 will be the same, because in 4-sided polygons also we are doing 1/3 part. So this will come as this. Generalize it, We only need, instead of this area, we need a generalized form. Rest is clear, I think. So k-sided m length regular polygon is, this is k plus 1, this is k. This is the formula of area for a m length k-sided polygon. M square k by 4 tan pi by k, 180 degree by k. And this will remain as the same. So it is very interesting to see that how different kind of uniform snowflake-alike structure grows if we start from a generic polygon, regular, and try to break its edges and appending a smaller structure of similar type as a hinge over that edges, and go on repeatedly doing it. You try to figure out one thing, that based on this recurrence, this is the area, right? So if my k tends to infinity, then it's almost a circle, right? K-sided polygon, if I have infinite sided polygon, it's a circle. So if k tends to infinity, can you see that your snowflake area, any n minus, so if you have infinite polygon or a circle, there is no edges to break. So what will happen? I am giving you just a question to ponder, that what will happen if the polygon is a circle? That means in your regular polygon k-sided form, k is infinity. Just think over it. So this is where we have used first order linear non-homogeneous recurrence answers to find out the closed form expressions. Now we extend it to second order linear non-homogeneous recurrences. So when I say second order, that means that only one term will be added to me, that is with I have Tn with Tn minus 1, Tn plus 2. So everything will remain same here, except for I have to consider here for distinct roots, equal roots and complex conjugate pair roots when we solve for the homogeneous part. I am doing here for distinct and equal roots, I am leaving for you to complete for the complex conjugate pair of roots. So now for the homogeneous part, you will have such kind of an answer as you all know and anticipate. For the particular part, again you can anticipate this way, but here you have to only consider that if everything is distinct from the distinct root, that is b to the power n is not equal to r1 as well as r2, then you can directly say this. If it is equal to some of them, then you have to extend it with n into b to the power n as per our concept. If this is not equal, if the roots are equal and they are not equal, b and r, then the same formula we can use. Otherwise, for equal roots, if I get the same thing, now see, for equal roots, I have already invoked linear independence by having one n into it. Now here I have to use an n square, because this is the minimum power through which I can have this solution as linearly independent than my equal root solution. So therefore, I have to do this as my answer. And again the same format will go. So the exact solution is the addition of all this. So the first one with this or this, the second one with this or this. Now the final thing is that you have to determine the constants and your unique solution finally by putting this each of them into the general form and solving for a dash and a double dash. Finally, with the base condition, solving for a1 and a2. All of these we have done over the examples and generic case. This one I have left for you as a final one. And the complex part I didn't consider. So you complete this whole generic second order linear homogeneous by your own with the complex root part as well, and also determine the constant and the unique solution in this process. Finally, an example. So you need to solve this kind of recurrence as we have seen. So our approach is first the homogeneous part, that is getting the characteristic equation x square minus 4x plus 3 equal to 0 gives me 2 root 3 and 1. Homogeneous solution is a1 3 to the power n, a2 1 to the power n. This part is minus 200 into 1 to the power n. So particular solution have to make linear independent. N into 1 to the power n into a is my particular solution part. So this is an. I put an directly in this equation to solve for a, that is an plus 2 minus 4 an plus 1 into a plus 3na equal to minus 200 gives me a equal to 100. So my final solution is a1 to the power n plus a2 1 to the power n, which is a2 plus 100n is which is equal to this one because I just put T0 and T1 to solve for A1 and A2. So this is your final answer. So if you see the last line, it just solves for A1 and A2. Okay, so this is how we solve for non-homogeneous equations, and here is a practical area where we get it. So we have computed nth Fibonacci number using the second order homogeneous form. But if we want to compute that, every time we compute nth Fibonacci number, we use one addition with the n-1 and n-2th Fibonacci numbers, we add them. So how many such additions we perform if I write a program to do that using this recursive formulation? So it is simple as per equation, that is an equal to an-1 plus an-2, that is computing the number of additions in Fibonacci number n-1, computing the number of additions in Fibonacci number n-2, plus the final addition to get my Fibonacci number n. And for 0 and 1 are my base Fibonacci numbers. I do not need any addition. I have direct answers for it. Hence, homogeneous part is just the Fibonacci recurrence to solve, and we have already solved it. Golden ratio to the power n plus beta to the power n and all that. Particular part, I have to solve it by 1 into 1 to the power n. So, a into 1 to the power n, nothing is 1 to the power n. So, I can keep it as it is, allowing the linear independence going. So, it is a. Putting it back, a equal to a plus a minus 1 gives me a equal to minus 1. Therefore, the final solution is this minus 1, where with a1 and a2 will be this, because if I put a0 equal to 0, a1 equal to 0, I get a1 and a2 as this. So, it looks a bit clumsy, but this is the number of additions we need to compute nth Fibonacci number using a recursive version. So that's why recursive version gives us exponential number of additions in your program, and your program becomes very expensive if you write it in that way. So today we have covered some kind of non-homogeneous recurrence and the way to solve it. So initially we started off with a generic form of higher order homogeneous recurrence solving, and then we extended it with the non-homogeneous linear recurrences of first order, and then followed up with the second order. The particular principle is that we will try to solve the homogeneous part, and we will try to give a particular solution. We will try to make both of them linearly independent. From the particular solution, directly mapping it in the expression of recurrence, we will solve the constant of the particular solution. Put up the whole solution, which is homogeneous part plus the particular part. Go for constant determinations by putting from the base conditions, and thereby finally getting the overall solution without the constant, which is the closed form, and all these examples showcases that. So in the next lectures, we will try to see what are the different variants or special kind of recurrence relations we have, and we will see how to solve them. Thank you.